Welcome to this lecture on linear data structures. We're going to introduce linear data structures, and we're going to talk about at least the first of three important ones: lists, stacks, and queues. So now that we've had uh, a hard look at analysis, let's dive into some real data structures. And we're going to start with linear data structures. And I know that at this point I start to lose people in the semester because I think people think, oh, I've already seen lists and stacks and queues. I know what they are. So this may be familiar to you, but I want you to stay engaged anyway, okay? Because we're going to discuss different implementations, and we're going to analyze these data structures more deeply than you probably have before, and we'll discuss different applications for these data structures. And I promise I will try not to belabor the points too much. A linear data structure, of course, is a container or data structure that keeps elements in a linear order. And all that means is that every element has a predecessor and a successor. Maybe not the first and the last, but after this week we'll spend looking at linear data structures and their applications. And then we'll spend the vast majority of our time looking at nonlinear data structures like trees starting next week and later in the semester. But let's look at the interfaces for the list, stack, and queue. The interface is really important, right? We have to know what are the methods that these types support that define the data structures. And I just out of interest, I've highlighted in red the names that are used by the C++ standard library. So the C++ standard library has a list, a stack, and a queue type. And they support the operations like if we want to insert into a list, it's called insert. But if we want to add to a stack, it's called push. And also for a queue in the standard template library, it's called push as well, okay? But we might call that enqueue just to be clearer that we're talking about a queue, okay? So these are the essential things that we talk about when we're talking about containers, data structures that are containers, that contain other things, are we need to think about what type of access do they have? Well, we know that a stack is last in, first out. We know that a queue is first in, first out. So first in, first out means that the earliest thing that was added comes out first. Last in, first out means that the most recently added thing comes out first. And a list, of course, has linear access. It's sort of a different category from FIFO or LIFO. So ignore that. I've just kind of grouped these ideas together in the idea that if you have a list, you're going to usually visit them one after the other. That's the intention, okay? But you can access any element, okay? With a stack, you can only access the top, and with a queue, you can only access the front. And that's what this says, right? The access for a list is any element. The access for a top is only the top item. The access for a queue is only the front item. Where can we add things to a list? Well, we can add things anywhere. We can only push onto the top of a stack. We can only enqueue or push to the back of a queue. And where can we remove from a list? We can remove anywhere. We can only remove from the top of a stack, and we can only remove from the front of a queue, okay? There are lots of data structures. There are other linear data structures that are equally important, like arrays and vectors, but we're not going to talk about these. Arrays have less formal semantics. So an array is sort of just a chunk of memory in C++ at least. And so we're not going to talk about that. And I'm going to assume that you know sort of what an array is anyway. And vectors are pretty much the same as what we'll talk about later in this lecture, which is a list that is backed by an array. Okay, so vectors are similar to lists if we implement them in a certain way. So we're not going to talk about vectors either. Okay, now we know the basic interfaces that we just reviewed for lists, stacks, and queues. What are the methods that they support? But what about the implementation for these data structures? Well, it turns out that each of these ADTs have in common that they could be implemented using an array or a linked list. And you might say, that sounds kind of weird. Why would I use an array for a list? And I want to point out here that the concept of a list, right, which is a linear ordering of things which I can visit or insert or remove from, is actually different than the implementation of a linked list, okay? A linked list is a linked list, but a list is not necessarily a linked list in all cases, okay? You could have a list which is implemented under the hood with an array. You could have a queue that is implemented under the hood with a linked list. So my point is that the list, stack, and queue can all be implemented either with an array underneath or a linked list. And using an array or a linked list does not affect their correctness at all. It should not, at least. But it might affect the performance of these data structures. And so that's what we want to look at is how do these data structures, how would we implement them using these two methods, array or linked list, and how does that affect the performance of them? And today we'll look at a list and we'll look at a stack and a queue in later lectures. So a list data structure, which we'll look at today, allows access to any element and insertion and removal anywhere at any time. But depending on the performance of the implementation, we have different performance for these operations, and we'll see that. In addition to how we implement it, also the way we use the list, regardless of how it's implemented, the way we use the list, the access patterns of how we use the list can also affect the performance. For example, if we are doing random access versus linear access. So the normal way to use a list is to go one by one, but we could just sort of jump around in the list. We could jump to the beginning and then to the end and then to the middle. That's random access, and that could affect the performance of our data structure depending on how we've implemented it, okay? So it's not just the implementation, it's also how it's used. So here I've put a linked list. So we're going to talk about a linked list implementation or backing for a list. Okay, so remember the difference. A list is a linear ordering of things, which we can visit any of them, and a linked list is a particular type of implementation. And we have two different types of access, which I just mentioned. We have random access and linear access. So we're going to analyze those separately, and we're going to look at how long does it take to insert, erase, or delete, or remove, or determine if it's empty. Now this here empty, this is not to empty the list, it's to determine if it is empty, okay? Now here's a pictorial description of what a linked list would look like. We have our front pointer and our back pointer, and both of those are members of the list data structure. And then the front points at a node, which points at another node, which points at another node, which points at this node, which points at nothing, right? It points to null, indicating the end of the list. Notice that this is a singly linked list. Okay, I could have described a doubly linked list. It's just that it crowds the paper or the screen, and it's a little bit more interesting actually to talk about singly linked lists. So let's look at each of these methods: random access, linear access, insert, erase, and empty, and determine what is the running time for each of these. Well, that requires us to think a little bit carefully about what the implementation would be using a linked list. And let's do this sort of in the easiest way possible first. The easiest method to implement is empty, right? To determine if this list is empty, what would be true? Well, it would be true that there are none of these nodes here, right? None of these nodes would be here. And so what would front and back be pointing to? They would both be pointing to null. So it's pretty easy to tell if the list is empty just by determining if front or back or both are null. So we can implement empty in order one time. Why order one? Because either front is null or it's not, and either back is null or it's not. And we just have to check that. And no matter how long the list is, you know, we could have one thing in our list, 0 things in our list, or 1,000,000 things in our list. It just takes a constant amount of time to determine if either of those pointers is null. I should also mention, we don't have to have the back pointer here, but it is convenient to sometimes have a back pointer if we want to append things to the back of the list. All right, let's do insert next, okay? Actually, let's do linear access. Suppose that we're starting at the front and we have an iterator or a pointer that walks from here to the next item. How long does it take to move this pointer, let's call that P, from here to here? Well, it requires going to the node, taking this value of next, and assigning that value of next into P so that P points here now. And how much time does that take? Well, I have to dereference P, I have to get the value of next, and I have to assign it into P. So that's 3 steps, right? Dereference P, get the value of next, assign that value to P. And so that's 3 steps, And those 3 steps, there's not more steps or fewer steps depending on how long the list is. So if the list has 10 items or 1,000,000 items, it's still just those 3 steps to move forward in the list. So linear access takes order 1 time to move from one node to the next. Okay? Let's talk about random access. How would I randomly access a node anywhere in this list? Well, if it's the beginning, that's easy. It would be constant time because I would just go to the front. If it's at the end, it's also constant time. But if it's somewhere in the middle, I'd have to start at the beginning and walk towards the middle, right? And so depending on how long the list is, that could be order n, because I have to take as many as n steps to get to that item. And it could be towards the end, it could be towards the middle. That's going to be order n steps. Okay, so you can see that these two have different performance. Just to get to one of those items, if I'm already right before it, it only takes me one more step. But if I am not anywhere near it, it takes me order n steps to get there. Let's look at the insert and erase methods. Okay, suppose that I want to insert, I'm gonna get rid of this and this. Let's suppose I want to insert something just after this node P that I'm pointing to with P. What are the steps to insert? Well, I have to create the node, right? Create the node. Then I'm going to have a temporary pointer to that node. Okay. And then I'm going to make the next pointer of this temporary node point to P's arrow next. Okay. So I've done 2 steps there. I've allocated the node and I've made T's next point to P's next. Okay. Next, what do I need to do? I need to make P's next point to T. So in other words, get rid of this pointer or replace this pointer with the value that points here. Okay. So those 3 steps essentially are what I need to do. I need to allocate the node, make the node point to what P was pointing to, and then make P's next point to that new node. And again, these 3 steps don't get slower or faster depending on how large the list is. So this is, if I already know where I want to insert, this costs me order 1 time. So that's good. Now, what if I want to erase something in the list? Suppose that I want to erase the thing that comes right after P in this case, the one that I just inserted. Well, I'm going to, again, I'm going to make a temporary pointer which points to that node. So I'm pointing at P, I'm pointing with P to this node. I'm going to go to the next node, which is the one that's going to be deleted. And the reason I'm starting from the one before it is so that I can update the pointers efficiently. So I go to P, go to the next node, make a temporary pointer that points to that node. Then, once I have this temporary pointer that saves the node, I can then change this point, get rid of this, change this pointer back to what it was before. Well, in this case, in this example, what it was before, to what T points to, right? So now P's next points to what T's next was. The next step is I might null out this pointer. Why would I null it out? Well, because I might have a cascading delete where if I delete this node, it deletes its next pointer, which would delete its next pointer, which I probably don't want to do. So I probably want to null out this node. And then finally, I can delete T, and that will get rid of this node. So again, I just have a handful of steps that I have to do in order to erase a node, the one after the pointer here for P. So that's constant time, and that constant time doesn't change if the list is very long or very short. Okay, so we have random access cost order n, and all the rest of these cost order 1. So this is pretty fast unless we need to do random access. Now this is for linked list backing of a list. Let's look at array backing for a list. Okay, now with array backing for a list, I'm again going to look at different types of access, but I'm also going to look at I'm going to look at random access, rather, inserting it anywhere versus inserting at the end, and erasing anywhere versus erasing at the end, and also determining if it's empty. Now, for an array-backed list, I'm going to have the array itself, its capacity, and its length. Now, what's the difference between capacity and length? Well, the capacity is 10 in this case. It's the size of the array. It's how much I can hold before I have to reallocate the array. And the length is how many items are actually being stored currently in the list. Okay, so how do I tell if this list is empty? Well, that's easy. I can just look at the length and ask, is it 0? And if it is 0, then it's empty. And if it's not 0, then it's not empty. So I can do that in constant time, no matter how long this list is. What about random access? What if I want to go to the 0th item or the 10th item or whatever? Well, again, because this is an array, I can do that in constant time. Now, because I can do random access in constant time, I can also do linear access in constant time, which is the nice part, which is why I didn't write separate random or linear access. So array-backed lists allow you to randomly look up things. Now let's look at the differences between inserting anywhere and inserting at the end. So if I insert anywhere, suppose that I have items here, 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 and here, and here, and I want to insert something, right here at element 2. Well, I can't just put something there, so I have to move these 3 items over by 1, right? I have to move those, let's see if I could, no, I won't do this, but I would have to move these 3 items, actually maybe I can't do this, let's try this. I would have to move these 3 items. Nope, that doesn't work. Those 3 items over by 1, such that 4 becomes 5 and 3 becomes 4 and so on, before I have a hole right here that I can use to insert something right there. Okay, so inserting anywhere in the list, especially if I'm inserting towards the beginning, is going to require moving enough data to make a hole, which could be order n things, and then putting that thing in. So this is going to be order n. But if I just want to insert at the end, right? If I just want to go to the length, the position at the length, which here might be 6, well, that's cheap. I don't have to move any data to do that. I could just append to the end very easily. So that's constant time. I don't have to move anything. So inserting at the end is fast. Inserting anywhere else might be costing me up to order n. And the same thing happens for erasing, right? If I wanted to erase this item, it opens up a gap, and I have to close that gap by moving everything to the left. And so that costs me order n. But if I just want to erase the last thing, then I can just decrement the length, and that costs me just order 1. Okay? So you can see, depending on whether I'm inserting in the middle, or the beginning, or at the end, or erasing somewhere in the middle, or the beginning, or the end, that gives you very different performance characteristics. Now, one of the things about an array-backed list is that if you have where the length reaches the capacity, then you have to increase the capacity. And for example, you could double it. You could create another array that's twice as large, copy everything from the old array to the new array, and then delete the old array. Okay, so here's a summary of what we've seen so far. We have different types of access. We have different types of removal, or I'm sorry, addition. No, this is for adding and removing, and this is for adding and removing only at the end. This is for anywhere, and this is for only at the end, right? A linked list, random access costs order n. Adding anywhere or removing anywhere in a array-backed list costs order n, and everything else costs order 1. Okay, so which of these 2 implementations, array or linked list, is faster? Well, the answer is it depends on how it's used. If you're doing a lot of random access, then clearly you'd want to use an array-backed list. But if you're doing a lot of insertions and removals from the middle, then you would want to use a linked list, okay? So the answer is it depends. They each have some advantages. Arrays don't use pointers, so they save memory that way, but linked lists don't use any more memory than they need to because they only have to have as many nodes as you have in the list. So next time we'll do the same type of analysis, but for lists and stacks. I'm sorry, stacks and queues.